Hi everybody, it's me, Mr. Olson, and I'm going to walk you through some very nice, very lovely stoichiometry problems. So let's go ahead and work through a few of these. These will not be questions from any assignments. These will simply be questions that I'm just giving to you so you can have the practice. And yeah, if you guys need to pause through the video, go ahead and make sure you hit pause so you can kind of catch up. I don't want to rush it, but I also don't want to go too slow. All right, here we go. The first question states, ammonia, NH3, is widely used as a fertilizer and in many household cleaners. How many moles of ammonia are produced when 6 moles of hydrogen gas react with an excess of nitrogen gas? So the very first thing we need to do here is we need to establish what the chemical formula is. They've kind of given one thing away, ammonia. We know that ammonia is going to be created here, and that is written as NH3. And we know that there's other things that have reacted to form what this is. So if we know we're going to form this, we can just have an arrow leading to it. And we know we're going to have two things. We're going to have hydrogen gas, which is written as H2. And then there's also nitrogen gas, which is written as N2. Most gases usually take like the diatomic form. That's why you have instead of just an H, you have H2. And I'm sure you guys are already aware of that. The next thing we need to do after we know what our formula is, because we've kind of done everything, we've got our NH3, we've talked about our nitrogen, and we've talked about our hydrogen gas too. So we're good there. Next thing we need to do is we need to balance the equation. In order to balance this equation, it's a pretty simple one. You could probably just do it in your head, but the balance is going to work out so that we have a 2 in front of the NH here, and we're going to put a 3 in front of the hydrogen here. And if we look on both sides of the equation, it kind of makes sense. We have 6 total atoms over here for hydrogen and 6 total over here on the right side. And then for our nitrogen, we have 2 nitrogens on the left side and 2 nitrogens on the right side. So we are balanced. We are happy. So whenever we're trying to solve problems using this process, and we're just starting off easy here, they always give you something that is known. Some people like to write this one way and just say, what's the known? What's the unknown? I like to write it this way, and of course you can do it any way you like, but the one thing they give us for certain is they give us the number of moles, which is 6 moles, of H2, hydrogen gas. We know what that is, but we're trying to figure out how to turn this information into figuring out exactly how many moles of ammonia are being made. So that's going to be a question mark, and we're looking for moles, and we're looking for ammonia, NH3. Now, for this problem here, you're not going to require the use of a periodic table, but whenever we do stoichiometry, we are going to have a periodic table handy. So if you don't have one, make sure you get it ready soon. So once I know what I'm looking for, all I have to understand now is that there are these things called mole ratios, and then there's molar mass ratios. And in this case, we only need to worry about mole ratios, and it's just a giant conversion factor, meaning we just got to turn information from one form into another. Yeah, it's a little bit of math, but it's nothing too terrible. So we know we're starting off with the 6 moles, so I go ahead and write there, moles of hydrogen gas, and then we're going to multiply by a conversion factor. Hey, look, pretty straight line. And the thing is, we want to get rid of the unit of hydrogen gas. We don't want hydrogen gas. We want this in ammonia. So what we do is we try to eliminate that unit. So we can go ahead and write down here that we want to get rid of H2, and we know that things will cancel out this way on top and on bottom of the fraction. Now, to figure out what we write here, we simply look at our balanced equation, and we're trying to find out the mole ratio between our different molecules that we have inside of our equation. So down here on the bottom, we're still working with hydrogen gas, and I look up here, and I find hydrogen gas in my equation, and it says there are 3 molecules of hydrogen gas. So I'm going to go ahead and put a 3 there. And then what we're trying to convert it to can go up top. Now, this process only needs the one step. So we're going to go ahead and write moles, and we're going to look for NH3. We're looking for ammonia. And if, once again, I need to know how many of these molecules I have in my equation, and in this case, I have 2. So I'm going to put a 2 on top of the fraction. And that's pretty much it. If we look, we're actually going to cross out these units of moles of hydrogen gas. And what we're left with are the only unit going to be moles of NH3. So I can go ahead and write moles of NH3. And I simply do the math, which is 6 times 2 over 3. You might even be able to do it in your head. If you need to use a calculator, don't feel bad, because I always need to use one too. And the answer would be 4. There are 4 moles of NH3. So do we now have an answer to the question that says that's asking for moles of ammonia? Yeah, we figured it out. And there you go. That's the first problem. All right, so the next question here is featuring pretty much the same idea, just working in a different direction. So it says the decomposition, which is interesting phrasing there, of potassium chlorate, or KClO3, into KCl and O2 are used as a source of oxygen in the laboratory. How many moles of potassium chlorate are needed to produce 15 moles of oxygen gas? Now, it might sound a little strange, but it's pretty much the exact same process to solve this problem. Just now, it gives us a hint for what that formula looks like when we're trying to write it. So the first thing we always want to do is, of course, write the equation. So this time they're saying we're breaking it down. So that means we simply start off with KClO3, and then we're going to have the reaction go this way, and we're going to break it down into KCl and O2 gas. Now, of course, we still need to check to see if the equation is balanced. If I just glance on the left-hand side, I see I've got 3 molecules of, I'm sorry, 3 atoms of oxygen, and on the right side we've only got 2, so we know something's not quite right. But this one's pretty easy to solve because I can kind of isolate my oxygen on the right side, and basically I can just kind of pin things down. You might be able to do it in your head. But when I look at this, I know whatever I do to the left side, I need to make sure I do to the KCl on the right side, because they're both in the same proportions already. They're already balanced. So quite simply, I'm just going to slap a 2 in front of this, which will give me 6 oxygen molecules, and then I put a 3 in front of my O2 to give me 6 oxygen molecules. But now my potassium and chlorine are all out of balance, but thank goodness they're isolated, and I can just throw a 2 in front of them, and we are good. So we have a balanced equation now. With that information, they did give us 15 moles of oxygen gas, or O2, and our job is to figure out how much or how many moles of potassium chlorate are there. So let's go ahead and do a conversion factor. Of course, we're going to end up on the bottom here with moles of O2 because we want to get rid of that unit. I look up to my equation to find out how many actual molecules of oxygen I have, and in the case over here that says 3, so I'm going to put 3 in there. Next up, what we're trying to convert to should be on top, and that means we're going to be looking for moles of KClO3, and we just look to our equation and we see that we have a 2 up there. That's where I got it. So we have our molecules, everything's in place. We can now cancel out our results there, and we end up with a pretty simple math equation: 2/3 of 15, or 15 times 2/3, however you want to phrase it. And that works out to be 10 moles of KClO3. So once again, the process is similar. Even if they are working in a different direction and the reaction goes in a different way, you can still end up creating an answer that's created the same way. Next question says, when magnesium burns in the air, it combines with oxygen to form magnesium oxide according to the following equation, which is 2M plus O2, which yields 2 MgO. What mass in grams of magnesium oxide is produced from 2 moles, which is actually 2.00 moles of magnesium? Now, once again, we're looking for something a little bit different here. Now our result, what we're looking for, are going to be in grams. So we are starting off with an equation already given to us, and thankfully it's already balanced just by taking a glance at it. But I like to make sure I still identify what I'm looking for, because now things can get a little tricky. I don't want to lose track of what I'm trying to do. What we're looking for are, what we started out with was going to be 2 2.00 moles of magnesium. And what we're going to derive from this is we're going to try to figure out what mass in grams of magnesium oxide we're trying to find. Like we don't know what this is, so we're going to try to figure it out. Now, all this really means is we're just going to add an extra step in our conversion factor, so it's nothing too crazy. But let's start off once again, keeping in mind we have a balanced equation. Let's start off with a conversion of having 2.00 moles of magnesium. And then we're going to go ahead and try to cancel out. We don't want moles of magnesium. We want something else. So we need to get rid of the moles of magnesium. So down here on the bottom, we're going to put moles of magnesium. And then how many actual moles do we have in our equation? Well, when I go up there, I see we have 2 moles. So I'm going to go ahead and put a 2 on the bottom. And then what I'm trying to convert this into is I'm just going to use a molar ratio. And I am going to convert this to moles of magnesium oxide. And the reason I'm going to do that is because I can simply convert my magnesium oxide mole into its mass. And I'll show you that here in a second. But I go back to my equation. It says I have 2 moles of magnesium oxide, which is good. Now you'll see here we get 2 over 2, which is 1. So it's a pretty simple little math step, but it's good to make sure we eliminate these units. Next thing we're going to do is we're going to try to convert this into grams, and all we have now are going to be moles of magnesium oxide. That's what we're left behind with from our last conversion factor. And by the way, we are crossing out those units now. We're left with moles of magnesium oxide. And in this case, we're just going to say, what's the weight? What's the atomic mass of all the atoms that are found in this if we only have 1 mole, 1 molecule? In order to find this out, we have to do a little side step where we go to magnesium and we find oxygen, and we literally go to the periodic table and find their mass. Now I've kind of jumped ahead for you here, but if you want to bust out your periodic table, you can. And I'm going to try to keep in mind that we have 3 sig figs and round up appropriately. But oxygen should be 16, magnesium will be 24.3, that is a decimal point there. And then we just simply add it together because they are magnesium oxide. They're combined with each other. And when we do that, we should end up with 40.3. That's a terrible 3, but 40.3. Now, that 3 might even be worse, but I don't care. And we're going to be looking for grams of magnesium oxide, which means now we'll be able to cancel out these units down here, and our final result will be what we're looking for, which is grams of magnesium oxide. Now, the trick is, once we get 40.3, we're simply going to do the math here. Now, if you look, it's actually not that difficult of a math problem. We've got 2, and then we've got 1, so 2 times 1 times 40.3 over 1, which is 40.3. So simply, you're just going to multiply by 2, but you will end up with 80.6 grams of magnesium oxide, which, if I've done my sig figs right, that should be correct. So that is that problem. Next question. Hey, look, it's a little bit of biology. Nice. So the question says, what mass of glucose can be produced from a photosynthesis reaction that occurs using 10 moles of carbon dioxide? Now, very kindly, the balanced equation was given to you. And by the way, like, if you remember in biology, if you ever took me, we actually did, I did show you a balanced equation of this. I didn't ever actually ask you to remember the coefficients, but certainly you should remember the formula. So it shouldn't be too unfamiliar to you. But main thing is we want to find out from 10 moles of carbon dioxide, what are we trying to get? Well, we're trying to find out the grams, the mass of C6H12O6. We're trying to find out the mass of sugar or glucose. So let's go ahead and start off our conversion factor. We're going to start off with 10 moles of carbon dioxide, and we need to get rid of that carbon dioxide because we're trying to turn this into sugar. So the first thing we're going to do is we're going to go ahead and put moles of CO2 down here. And then we're going to look to our balanced equation already and find our CO2. and it says that we have 6 moles here, so we're going to stick in a 6 down there on the bottom. And then above, for our portion, we're going to convert this into moles, but we're going to convert it into moles of C6H12O6. Now I just look at my balanced equation. There's no coefficient there, which means there's only one. So there's only one molecule of sugar produced in this reaction. And then we are going to convert this, because we don't want moles of sugar. We want it to end up with grams of sugar. Yes, I'm writing the whole thing out. Deal with it. So how many moles do we have? Well, we're only going to look at 1 mole at a time, because we can determine what the mass of one individual molecule is going to be by using the periodic table. So to figure out what the grams are up here, we have to do a little bit of more math off to the side. So we're going to have 6 carbons, we have 12 hydrogens, and we have 6 oxygens. So we need to know the molecular weight of all of these wonderful, wonderful, wonderful molecules, which, if I'm being lazy, which I totally am, I've already looked ahead, and I'm going to tell you that the molecular weight for carbon is going to be at 12. For hydrogen, it's going to be 1, or at least really close to it, and for oxygen, it's going to be 16. And then we need to multiply our numbers here. So if we end up with 6 times 12, which because we have 6 carbon atoms, 12 times 1, and 6 times 16, if you add that all together, you should end up with 180. Or at least really darn close to it. And that's what we're going to shove up at the top of this equation. Once we do that, we will end up with our proper units, because the moles of carbon dioxide have canceled out, the moles of sugar have canceled out, and we're only left behind with the grams of sucrose. I'm sorry, of glucose. So the math basically works out that we have a 10 times 1 over 6 times 180. And when you plug that in there, you should end up with a number. Sorry, checking numbers. Sorry, I had to pause there. We're going to end up with a number that should be 300 grams of C6H12O6. We should end up with 300 grams. So there you go. This problem is actually rather similar to one of the problems, or 2 of the problems that you guys are working on, but not the exact same thing. Honestly, we can just change a few molarity numbers and we end up in a totally different place. But anyway, there you go. Okay, so looks like a scary question, but I promise you it's not so bad. Question says, oxygen was discovered by Joseph Priestley in 1774 when he heated mercury 2 oxide to decompose to form its constituent elements. How many moles of mercury oxide, HGO, are needed to produce 125 grams of oxygen, O2? And also, how many moles of mercury are actually produced? So I look at this and I see, hey, there's 2 parts, an A and a B. So let's address each one individually, which should be pretty simple. So first off, we have to create our balanced equation. They give us that it's a decomposition, so we're starting off with a bigger molecule and we're going to break it down to smaller ones. They were nice enough to tell us HGO is mercury 2 oxide, and then we have yielding, or we are going to yield the gases O2 and mercury, just the element itself. Now remember, oxygen itself is found in a diatomic form, so you're going to find it as O2. But if we know that, we just have to look and we have to make sure we're balanced. Oh no, we're not balanced, but it's a pretty easy fix. I have 2 oxygens on my right side, 1 on my left. Well, I'm going to go ahead and throw a 2 in the front. Now I got 2 oxygens on the left. Everything's good, but now I've got too many mercuries on the left, so I will simply just add a 2 in front of that. So we've got a balanced equation. Everybody's happy. Let's do this thing. They give us one piece of information, and they give us 125 grams of O2. And our job is to convert that so we can make, or at least we can find out, how many moles of mercury oxide there are. So we need to figure out moles. So we started in grams, which is a little strange. We're kind of going in reverse order here. which honestly all we do is just reverse everything. So if we look at O2, O2 is oxygen is its weight is going to be at 16. We're simply multiplying by 2, so it'll be at 32 grams of O2 down here. And that's going to be per mole or per molecule of O2. So we can see our units are going to cancel out down there. And then we are going to go ahead and say we need to look at our actual equation, and we're going to look at how many moles we actually have of oxygen gas. Well, we only got a blank there, so that's just going to be simply 1 mole of O2. And we look up, and we're trying to convert this into how many moles of HGO we have. And our mercury 2 oxide is going to be found with 2 moles. And then we just simply multiply it, which is 125 times 1 over 32 times 2, which is a pretty simple math equation. And when you run those numbers, you end up with a wonderful number, and I'm rounding here, 7.81 moles of HGO. And that looks like my answer to part A. We've done a good job. All right. Now, if you are a very sneaky person, you probably noticed this already, but the next question is very, very easy. But we're going to work through it anyway because that's the way you should do it. You should always test everything before you just guess. Anyway, we only start off with one piece of information, 125 grams of O2, and then you are simply going to have 32 grams again of O2. You're going to have 1 mole of O2, same reason that we did it back there. This is the only place where we could potentially see change. We're looking at the same formula, so we have 1 mole of O2, and we look for now what we're trying to find out are going to be how many moles of mercury there are, so moles of mercury, Hg, and if I look, okay, I find it's a 2. Oh my gosh, it's the same thing. 7.81 moles of now, Hg. So that would be your solution to part B. And look at you, you did it. Once again, guys, you got to make sure you run through both things. If you just would have assumed something, you could have ended up in a pretty weird place. So always test. Always try to figure it out. Final question I'll run through with you. What mass of aluminum is produced by the decomposition of 5.0 grams of Al2O3? So it's a decomposition. I know I'm going to have Al2O3, and that's going to break down to form basically its constituent elements. It's going to make aluminum, which is just aluminum by itself, and it's going to make oxygen gas because, once again, oxygen likes to do that. It likes to take a gaseous form. So if we look at our equation, no, it's not quite balanced. That's not a good thing, which means we get to have a little bit more fun with it, but that's fine. That's okay. The first thing I do is I look on the left side. I see I have 2 aluminum, and I see, oh, I've got only 1 aluminum on the right side. I've got 3 oxygens on the left side, 2 oxygens on the right side. I love to tackle my odd numbers first. So what I'm going to do is I'm going to multiply this side by 2, which would give me 6 oxygens on the left side. I can easily fix that on the right side by adding a 3 in front of our oxygen gas. And then I just simply look, how much aluminum do I have on the left side? Well, I've got 2 times 2, which is 4. And then I can just slap a 4 on the front there, and everybody's all happy. So we've got a balanced equation. We know what we're looking for. We've got 5.0 grams of Al2O3, and we are trying to figure out how much aluminum is actually being produced. So what we're going to do, wow, that's a terrible line. Let's try that again. Not much better, but that's okay. First thing we're going to do is we need to find out the actual mass of Al2O3. And I once again have kind of jumped ahead for you and done a little bit of math. But that's fine. I saw it was 26.9. That's the mass of aluminum. And I multiplied that by 2. And then I looked ahead and I got 15.99. And that was my mass for oxygen. And I multiplied that by 3. When you add that all together, you should end up with 101.93, which is going to be grams of Al2O3. And then we need to look at that and we need to say, well, that means it's going to just be 1 mole of Al2O3. And then we can convert this again. We've got ourselves a nice little run. And at this point, we can actually look at the equation to fill out what we're going to do here, the actual mole ratio. And we're going to have 2 moles of Al2O3. And we're going to try to convert this, what we're actually looking for, into aluminum. So we're going to turn this into moles of aluminum. And if we look in our formula, we get 4. So we have 4 moles. And then we will do one more step, the final step, I promise. Now we are going to stretch this out. We are looking at 1 mole of aluminum, and we're trying to find the mass. We're trying to find the grams. So we're looking for a weight, grams of aluminum. And we're going to have to do a little bit of math off to the side. And we said we have 4. Because I'm crazy. We're not looking at that. My bad. For every mole, we know how much weight is in 1 mole. It's just simply 26.9. And then we've finished. We've got a solution there. So I know it doesn't look like it, but it's 5.0 times 1 over 101.93 times 2 over 4, which is 2, times 26.9. So once you plug that into your calculator, you should end up with a number that is very close to 2.6 grams of aluminum. Very, very, very simple once you know the process. So I hope that was helpful. If you guys have any questions on your assignment, we have some keys in place, so we can kind of help you out. But really, you might have to struggle with it, but you know, ask a neighbor, see if you can help each other out, and actually try to learn the process. All right? Thank you.